Okay. So, yesterday we saw how we can simulate galvanostatic measurements using numerical methods, right. Today I want to show you how we can simulate instabilities, in particular potential instabilities. Okay. We assume that normally the DC potential or the open circuit potential does not change with time, but in many cases open circuit potential will drift and it will come to a stable value after some time. It may be few seconds, few minutes, or in some cases it can take hours to stabilize. Okay. So, what I want to show you here is an example for a two-step reaction where the open circuit potential changes with time. It can change linearly, it can change exponentially. I want to also show you examples of what I mean by exponential. We will see quickly how the results will come for a simple electron transfer reaction. Later I want to show you an example with code of how to handle it when you have potential drift. You can of course use the same concept when you want to simulate cases where concentration changes with time. All these things basically mean when you do an experiment, at the end of the experiment the system has not come back to the original state. So, it is not a stable system. In this case we deliberately introduce a potential ramp or potential change, but what we want to mimic is in real life if potential changes not because we want to change, but because the system itself is not stable. In those cases if we know that this is how the potential changes with time, but still we acquire data, we acquire EAS data during the time when the potential changes, then what should we expect to see? That is what we want to see here. Okay. We have done some of this work and published this in 2011. So, the idea is what happens if the open circuit potential changes linearly with time. So, in that case our initial potential is given by E in it, whatever we would consider as DC potential, that I call it as EDC prime because it is not really independent of time. We denote it as a prime to indicate that it is not normal EDC. So, initially let us say that this is our DC potential, this is OCP, open circuit potential, this is potential with respect to time. If open circuit potential were independent of time, it will be a constant, and this may be for example 0.2 volts versus our reference electrode AgCl or any other reference electrode, and then we are at the potential which is 0.3 volt above the open circuit potential, which means it is 0.5 volts versus our reference. Now, this is the case if we have a open circuit potential that is independent of time. If the open circuit potential decreases with time, then we are maintaining 0.5 volt with respect to the reference electrode, but that is not 0.3 volt versus OCP, that is actually changing with time. We would call that as 0.3 volt plus AT, where A tells the rate of change of open circuit potential with respect to time. If that is decreasing, we will say our actual potential where we maintain that is increasing with respect to open circuit potential. Okay. So, this is one example, and this probably works when it changes linearly with time. It changes at a slow rate, but over a period of time it continues to change. It is not likely, in practical cases it is not likely that it will change linearly at a fast rate and continue to change linearly. Okay. So, this is one possibility. Another possibility is this: a lot of times we will see that the potential changes quickly for some time and then it will come and stabilize. It may change like this and come and stabilize, it may change like this and come and stabilize. This would be potential with respect to time. So, initially it changes quickly and then later it changes slowly. This one can model using an exponential decay given by an expression like this. This is the change, this is the initial value. E delta specifies the maximum possible change if you wait for infinite time or long enough time. This defines how rapidly it decreases or changes. Okay. So, it is given by exponential minus Bt, B is the parameter here, and E delta tells the maximum possible change. So, in some cases this is probably a more realistic representation of what actually happens in a cell. In case I apply a sinusoidal potential when you have a linear change in the open circuit potential, our DC potential is 0.3 volt with respect to open circuit potential, and if the open circuit potential were to remain constant, this light grey color line would represent that DC potential with respect to open circuit potential. When the OCP changes with time and it decreases with time versus OCP, the potential DC potential actually increases, and if we superimpose an AC on top of it, right, the way we would do the measurement is initially we would apply a high frequency potential, then we will go to little lower frequency and so on. This is typically how the AS spectrum is measured. Okay. This example, let us just pretend that we are applying only one sinusoidal wave, we are acquiring the current, and we will later do Fourier transform and calculate the impedance. So, if you are applying 10 power 1 hertz, then 10 power 0.9, 10 power 0.8, this is logarithmically spaced 10 frequencies per decade, but we have a change in the open circuit potential. So, that change is given at the rate of 0.01 volts per second, that is 10 millivolts per second, which is actually fairly large change. But I just want to show you how the potential wave will appear, and if I continue to apply lower and lower frequencies, it will continue to drift like this. So, it is not going to be sinusoidal wave at a 0 bias or at a constant bias, the bias is changing. In case the actual change in open circuit potential is described better by this exponential change, this is what we would see. If you apply sinusoidal potential, this is what we are applying, and you can change the frequency, another frequency, and so on. So, initially you see a rapid change in the bias, and later you see a gradual change in the bias. Now, you can consider any mechanism. Right now I am considering two different mechanisms. One is the simple electron transfer reaction, second is a reaction with adsorbed intermediate. If you can handle these two, you should be able to handle any other reaction. Okay. So, if you have an electron transfer reaction and if the DC bias changes linearly with respect to time, I am not going through the full detail, but basically what we would do is to apply this, measure the current, and remember at the end of this first cycle or n number of cycles, the DC potential starting point is different now, and then again apply a sinusoidal potential along with the ramp, measure the current, perform FFT, calculate the ratio of potential to current and call that as impedance. Then remember now the potential has shifted again. If you do one cycle, it has shifted by that period. If you wait for n number of cycles and then perform measurement for n number of cycles or m number of cycles, you have to wait for so long, that means the DC potential has shifted by that much. So, all these things have to be taken into account. If I have very slow change, 10 power minus 6 volts per second, that means few hours to get few hundred millivolts, then the spectrum will appear more or less same in this scale. If you go from 0 to 200 ohms, if you really zoom in, you would see that the one which is stable settles here, the one which is unstable or drifting, or we call it as instability, potential ramp, that shows there is a small movement here or small change here. It continues to move towards the origin. So, there is a difference, but it is not very perceptible, and if you have experimental data with noise, you may not see that difference clearly. Now, what happens if the ramp rate is little higher, that is 10 power minus 5, 10 microvolts per second, that is actually quite possible. What you would see is at high frequency and mid frequency you would not see any difference, okay. But at low frequencies it increases. It is not a 45-degree line, it increases, but at a very low angle, it continues to increase, okay. So, if you are not careful, this is for one set of kinetic parameters, right. If you have another set of kinetic parameters, another DC bias, another ramp rate, it is possible that it will appear somewhat like Warburg impedance. Okay. One has to be careful. At the end of this measurement, if you restart and continue this measurement, take the spectrum again and compare with the first spectrum, do they match? That is one way to check for repeatability, that is one way to check for any changes in the system, is it stable or not stable. Here of course, the instability it does not arise because we are applying the sinusoidal potential. There is systematic instability, it is just that if you are not aware of it and you take measurement and analyze it assuming that the system was stable, then you will end up with wrong interpretation. You might in this case end up with the interpretation saying diffusion is contributing to the system or it may be rate limiting. Of course, it is not a 45-degree line, so you should not get that interpretation, but just to warn you about this possibility. What happens if the potential change is actually exponential? Okay. With a maximum change of 10 millivolt and a maximum change of 100 millivolt, the 10 millivolt results are given as blue filled circles and the 100 millivolt results are given them as diamonds with brown color, and the stable result of course will start here and end at this location as a semicircle. In both cases, even if there is a 10 millivolt change and there is a rapid change in the beginning and slow change later, you would see that it is moving towards the origin, and if it is 100 millivolt change, it is moving to a large extent. Okay. This tells you the rate at which it changes. It is not exactly dE by dt, but if the parameter b is large, it means it will rapidly come to the final value. If the parameter b is small, it will take long time to come to that final value. Okay. It can be thought of as inverse of time constant. Okay. Now, instead of increasing the DC bias with respect to open circuit potential by 100 millivolt, if it changes in the other direction, if it decreases, what would you see? Now, I have told you that all the time you should plot the abscissa and ordinate in the complex plane plot at the same scale, but sometimes it is better to plot this with different scale, but clearly mention that the scales are not equal. So, here I have plotted 0 to 1500, 0 to 100 in this scale. It does not appear as a semicircle, although if you really plot with equal scale, it will appear more or less like a semicircle here for the first part. The stable results basically show a semicircle and end here. The unstable result, if I draw it in the correct scale, it will probably look like this, a semicircle and a slight change. I am again exaggerating here, a very slight change, increase and then decrease and settle down. Again somewhat like finite Warburg impedance, but not really going at 45-degree and coming down, instead going at a very slight angle and then coming down. But if one is not careful, they might come up with the interpretation that there is a mass transfer effect and this can be modeled by a finite Warburg impedance. Of course, it will not model correctly. If you take finite Warburg impedance and apply it here or use a circuit and fit it, it will not apply correctly. But first thing you need to check is the open circuit potential drifting. Is the concentration the same at the beginning of the experiment and at the end of the experiment? Okay. Does the surface look the same? Is it the same from the beginning to the end? If there is a change in concentration, if there is a change in the surface, then open circuit potential can shift, or even otherwise the reaction rate constant can change. Okay. This example we illustrate with the change in DC potential, but you can also incorporate the effect of changes in concentration, effect of changes in rate constant, effect of changes in area, as long as we go with the numerical method. If you want to use analytical method, it is possible only for a simple electron transfer reaction. For small changes in this drift, for small EAC 0, if I want to apply for large EAC 0, I cannot use this method, whereas this numerical method can be used for arbitrarily large or small value of amplitude, small changes or large changes. Okay. So, it is lot more general, of course, it is more time consuming in terms of computational time. So, one of the interpretations is that the patterns that you would get when you have instability, they are qualitatively different. It is not just a semicircle which is slightly larger or smaller, it is a semicircle with other features, okay, and which can lead to incorrect interpretation. Now, I want to show you how we have done this for a two-step reaction, where you have an exponential decay. Okay. The reaction is of course something we have seen many times, we are familiar with this. This is metal going to metal adsorbed and metal adsorbed going to metal 2 plus electron. So, the first and second are electron transfer reactions. Mostly we have seen the reaction where the second reaction is a chemical reaction, the first reaction is an electrochemical reaction, and maybe one or two examples we have seen with both steps being electron transfer reaction. Okay. So, what this means is the current, Faraday current, it has an expression which is F k1 1 minus theta plus k2 theta. Of course, the mass balance equation remains the same. Initially, we will give the kinetic parameter values. We have chosen certain set of kinetic parameter values. We can note them down. Because the second reaction is also electron transfer reaction, the exponent corresponding to that rate constant is not 0, it can have a positive value. We have gamma, DC potential in the beginning is 0.3 volt with respect to open circuit potential, and the maximum, if I want to find the stable result, I can still use the same code and say that the drift is 0, E delta is 0, or I can say it is plus or minus 0.1 or whatever voltage I want to specify, I can put there, and this B is the drift, it is not related to the B1 and B2 that we used in the rate constant. AA capacitance, of course, I assume it to be 10-20 microfarad per centimeter square, something that is reasonable, and this example I have shown it with 10 millivolts perturbation amplitude, but you can use the same code with a larger perturbation amplitude and you would get the results anyway. So, we specify the kinetic parameter values, we choose the frequency range, we start at 10 power 4, that is 10 kilohertz, and end at 1 millihertz at this specified interval. Okay. So, it is going to go logarithmically spaced or geometric spaced 10 frequencies per decade. Now, you can understand, if I give 10 frequencies per decade, it is going to make measurements from 10 kilohertz, it will take certain time to come to 1 kilohertz, then 100 hertz and so on. If I use 5 frequencies per decade, I will come to the 1 kilohertz fast. That means my measurement time is less, which also means I am definitely not taking so much time to complete this, but at the end the DC potential at the end of this experiment. So, if I do one set of experiment with 10 power 4 5 frequencies per decade and another set of experiments with 10 power 4 10 frequencies per decade, it will take longer time for us to complete the second experiment, it will be faster to complete the first experiment, and because there is a drift, we will end up at one DC potential here at the end of this experiment, and we will end up with another DC potential here at the end of this experiment. When I say we will end up at one DC potential, I mean with respect to open circuit potential. With respect to reference electrode, the instrument will control and it will come to the original potential with respect to the reference electrode. When the open circuit potential changes with time, with respect to OCP, the DC values will be different at the end of this experiment and it is going to be different at the end of the second set of experiments. So, it is not just that how fast does it drift, it is also how long do we take to make the measurements, that plays a role in how the spectrum will appear. So, that is another way. You can have one fine intervals for the frequency and one coarse intervals for the frequency and fine intervals for the frequencies, and do two sets of measurements. If they are more or less overlapping, then you can probably say that drift is not that significant. within the experimental level, right. If they are quite different, then this is one thing you need to consider. Okay. When you want to account for the potential drift, you have to have a variable saying how long is it from the beginning of the experiment. So, we call it as time from start, set it to 0. First, when you apply a sinusoidal potential in the very beginning, there is no drift, meaning you are starting at the right potential, whatever you want to start at, you are starting at that potential. And then second frequency onwards, you will have to remember that with respect to time, the DC potential has changed. Because the time has changed from 0, the DC potential has changed. So, we say duration is the period for that particular frequency. Okay. So, initially we apply 10 power 4 hertz, that means 10 kilohertz. So, we have waited for some time to complete at least one cycle. So, now the time from start is whatever time we have waited before plus the period of last perturbation. If I apply n number of cycles, I need to multiply this by n. If I am applying only one cycle, in this example I am assuming that I am applying only one cycle, I am not at all waiting. As soon as I apply one cycle, I take the data, go to the next cycle, okay, which is probably not what the instrument does. If you have to wait for some time, in the simulation also you have to say wait for that time. That means you apply sinusoidal potential, the DC potential keeps changing during this time, and then you apply sinusoidal potential few more cycles, hoping that these are steady periodic, because we do not know. We assume that DC potential is stable, we assume that the response has come to steady periodic, although in the simulations we have to recognize that it has not come to steady periodic. And then at the end of it, the DC potential has changed so much, and then we have to start at the new DC potential. Okay. We set these as variables, pass it as a vector, and then supply it to a function which we call as nonlinear unstable, and this is denoted as mechanism 1. We need to integrate this equation, we need to specify what is the theta steady state, and that theta steady state is going to change because the EDC is changing. So, every time you need to calculate the new theta steady state and then send it as initial value. If DC potential is slowly changing, we assume theta is also slowly changing, and we can call it a pseudo steady state. Right now we are calling it a steady state. So, we get the k10 exponential b1 e, but the e is different compared to the initial value. E depends on the EDC, and then it is specified by e delta 1 minus exponential b time from start, how long we have waited, and likewise for k2, and this can be integrated. After we integrate, we get the value of theta, and then you can calculate the current by using this expression. If you have theta as a function of time, you can generate anyway E as a function of time. Just remember you have EAC, but E is EDC plus drift plus EAC. So, it is not just DC plus sign, it is actually DC that is changing plus sign. Okay. And then once you know the E as a function of time, you can calculate k1 and k2 as a function of time. The integration has given us theta as a function of time. So, we can calculate the current and then perform the FFT. So, for the integration we have passed on these parameters, we calculate the theta using this equation. D theta by dt is given by k1 minus k1 plus k2 theta. Yeah, this is correct, okay, and this has to be divided by gamma value. Only thing you need to remember is E value, do not write it as EDC plus EAC, instead remember to write that this is a function of time given by E drift, E delta 1 minus e power b t, but here the t is time from start plus whatever time we are using in the integration. So, if you want, you can note this down. So, it is not just taking the formula and applying directly and using e power minus b t. You have to recognize that when you are applying some perturbation, you might have applied some perturbations before and that would have taken time. So, the DC potential has changed, and in addition you are changing when you are applying the sinusoidal potential and measuring, that time also that DC baseline is not constant, it is changing. And at the end, of course, we have seen this, you can do the Fourier transform, calculate and get the value of IS 0, measure the value of phi s is 0, you are multiplying by 2 as usual, adding pi by 2 for the phase, you can calculate. So, essentially what we are doing is mimicking what the instrument would do. In the equipment, if you say that measure the open circuit potential and then apply a bias of certain voltage above or below the open circuit potential, the instrument will still regulate the potential with respect to the reference electrode. Just before starting the experiment, you can ask it to measure the open circuit potential. So, it might say 0.2 volt with respect to reference, and then if you say 0.5 volt with respect to open circuit potential, it would apply 0.5 volt plus 0.2 volt. So, it will apply 0.7 volt with respect to reference electrode, but it does not monitor how the open circuit potential changes with time or whether it is remaining constant or not. Okay. So, you would get results which would be given by this if the potential was drifting. Okay. So, if you take the system and monitor the open circuit potential and you find that it is changing with time and it does not settle quickly, and you want to do impedance experiments before it settles, then the instrument would give you results which are given by this code, provided this is the mechanism and these are the kinetic parameters. So, in this case, for a set of kinetic parameters which we saw before, if there is no drift, what you would get will be a high frequency semicircle and a low frequency inductive loop, high frequency capacitive loop and a low frequency inductive loop. If I have exponential change in the DC offset given by this number 0.002 second inverse and 100 millivolt plus 100 millivolt, instead of settling here it would drift. So, it would appear like a capacitive loop, an inductive loop and sort of an inductive loop. It is not really a clear inductive loop, but it looks like it is another loop here. So, this means open circuit potential decreases with time and it can eventually settle at 100 millivolt less than what it started at. It is also possible that the open circuit potential will increase with time, which means the DC potential versus OCP is going to decrease, DC bias versus OCP is going to decrease, and you can do the simulation with minus 100 millivolts, and what you get is a capacitive loop, an inductive loop which does not complete, instead it turns and goes like a very large or pushed down capacitive loop. So, it is not as clean as coming here and coming like this, looks like this, and from here it is still below the x axis, but it is a very gentle curve. Again, if you see something like this, of course, you will have to do the other checks. If you see something like this, you cannot always assume that it is because of drift, but you should not come to a conclusion that this means there is one more capacitive loop, that this is specifying the charge transfer resistance in parallel with double layer capacitance. This inductive loop means there is a adsorbed intermediate. If this is a capacitive loop, that would mean there is one more adsorbed intermediate, whereas we know the mechanism says there is only one adsorbed intermediate. So, you can't come to that conclusion. You can't also come to the conclusion that this is necessarily due to drift unless you do what? Unless you do KKT validation. Okay. If you do KKT validation, all the spectrum which arise with instability effects or which are coming from system which are not stable will be flagged correctly. So, if we change the kinetic parameter values, for example, Same mechanism, just a slight change in the kinetic parameter value, maybe a different reaction, different concentration of chemical, different DC potential possibly. No drift, I see 2 capacitive loops. So, same mechanism, just change in kinetic parameter value. Of course, you can get inductive loop or a capacitive loop because you have an adsorbed intermediate. No drift, I have 2 capacitive loop. This of course comes from charge transfer resistance and double layer capacitance. This comes from the adsorbed intermediate species. Of course, here I have simulated with 10 millivolt, but you can also simulate with 100 millivolt. The methodology, numerical methodology, does not require that this perturbation potential has to be small, it can be large. And similarly, you can get the second and third harmonic and other harmonics, it is not at all a problem. Right now, we are mimicking experimental measurement of impedance spectrum using normal equipment, which may or may not be able to give you high harmonics data, but this methodology, it is pretty straightforward to get the high harmonics data. Okay. And I am showing this in the nonlinear AAS section because the code that we use is meant for nonlinear AAS. You can use it with small amplitude perturbation and get the response at linear regime. Okay. It is more general compared to what we have done in the earlier classes. In the first 10 weeks, we have focused on linear traditional AAS. So, you can't take the results there and directly get the results at the larger amplitude. Now, if there is a drift, you can guess how it is going to appear. It is not going to look like this, right. So, if there is a drift where the open circuit potential decreases with time, that is DC bias versus OCP increases with time, we see something similar to an inductive loop, not a clean capacitive and inductive loop. Instead, it looks like a distorted inductive loop, if you will. And if the potential change is negative, you can guess it is going to be one loop, second loop, and a poor distorted capacitive loop. That is one way to look at it. It is not the correct way, but one might interpret it like this if you are not careful. Okay. So, in summary, you can use the numerical method and modify and account for changes in potential. What we have seen is changes in potential, but I also claim that you can do this for changes in surface area, you can do it for changes in solution concentration or rate constant by some effect. This change in potential during the experiment results in what appears to be a distortion. Okay. You are not just going to get the same pattern with a slightly larger or smaller value, you are going to get a different pattern, which can lead to misinterpretation if you are not careful. Okay. And the right way to handle this is to first validate all the data with KKT and then analyze the data which passes this KKT test. If it does not pass KKT test, it is better to repeat the experiment and see if you can get stable system, wait for sufficient time and do the experiment, and if you cannot wait, then you might have to do simulations, numerical simulations like what we have shown here, and then see if it matches with the experimental results, and if it does, then you will have to say, yeah, probably there is a drift. We will stop here today.